Welcome, I'm Professor Nathan Weezy from Marquette University. This section we're going to talk about the introduction of continuous control and a bunch of the basics that we're going to use throughout these series of lectures. All right, so the first things first, everything's really going to be based back from your Circuits 1 and 2 course. We're going to be doing a lot of work in the frequency/S/Laplace domain. This right here, equation 1, is essentially the definition of the Laplace transform to convert a time domain signal to the frequency domain. So everything is going to be based upon this. Now, what we're going to deal with a lot when designing controls in control systems is dealing with functions in transfer functions in the S domain. So a lot of times we're going to get rational polynomials as fractions like this. So you have x of s, which is generally your input, y of s, which is your output, and g of s is your transfer function from input to output. And what you'll get on both the numerator and denominator are rational functions, rational polynomials, shall I say, of s. And essentially these are just two sums summing from 0 to n and m respectively with these coefficients bk and ak in front of it. So you'll get some rational polynomial, for example, like s plus 1 over s squared plus 6 s plus 2. There is a polynomial in the top and bottom, and this would be a transfer function in the frequency domain. Okay, so next thing is, okay, so you can actually take this transfer function and you can factor it. And if you factor up top, what you will get are zeros of the transfer function because those numbers actually drive the function to actually 0. And then the zeros of the denominator will actually shoot towards infinity, and we call those poles. So zeros of the numerator, they're called zeros, and zeros of the denominator, these are called poles. This is really important because what will happen and what we'll see here shortly are that poles are really going to dictate the type of response that you're going to get, whether it's underdamped, overdamped, what your damping ratio is, the damped frequency, the resonant frequency, the Neper frequency, all that stuff is going to be dictated by your poles. And what will happen is the zeros, a lot of those will dictate like your initial conditions. Okay, so let's consider this. Consider this transfer function written here in equation 4. Don't worry about the numerator. Let's just focus on the denominator. In fact, what you can do is you can write, using the quadratic equation, the solution for the two zeros in the denominator, which we'll call poles. And if you do that, what you'll get here is equation 6. Okay, minus alpha plus or minus the square root of alpha minus omega naught squared. So alpha is called the Neper frequency, and omega naught is the natural or the resonant frequency. So it gives you an idea of how those things play around. And depending on these values, you can get only real numbers for poles, or you can get a complex conjugate pair for the poles. It just depends on what alpha and omega naught are. Now, you could do some rearranging. You can define omega d, which is the damped radiant frequency, as the square root of the resonant frequency squared minus alpha squared, and then you can rewrite the poles again in this form. Essentially, equation 8 and equation 6 are the same. It's just depending on what you want your equation written as a function of. So 8 is the poles in terms of the Neper frequency, alpha, and the damped radiant frequency, omega d. Now, this form is generally very nice if you want to know exactly what the time domain response will be, because alpha, or the Neper frequency, is basically the decay rate of your exponential, and omega d, the damped radiant frequency, is the frequency at which an underdamped response will ring at. Okay. All right. Now, another way you could define it would be equation 5. And let me use a different color here. If you define it as equation 5, again, this is pretty much the same thing. We're just using different variables to describe it. We now have this zeta factor, which we'll call the damping ratio. And we have omega naught, which is our natural frequency or resonant frequency. So we can write equation 9 by relating 4 and 5 together. So essentially zeta is alpha by omega naught. And then we can write the solution again for equation 5 in terms of the poles of the denominator and come up with 10. Okay, so what does this say? Well, 10 is essentially saying the same thing as equation 6 and 8, but just, again, as a different variables as your input. This zeta damping ratio and omega naught natural frequency essentially is information of the poles. Zeta, the damping ratio, will tell you how much damping you have as a unitless number, and omega naught is the resonant frequency. And what you'll see is if you look at 10, as long as the damping ratio is between 0 and 1, this poles will be a complex conjugate pair. So we'll write this down. So when zeta is between 0 and 1, that gives us complex conjugate poles. And you can see that on the right-hand side there. All right, this is actually really useful because what this says is if you have more than a damping ratio of more than 1, then your roots or your poles will be real numbers, which means that you will have a overdamped response, which means there'll be no ringing in response. Okay, great. That's pretty informational. So what we're going to do is take this stuff now, and we're going to go ahead and look at some sample equations. So equations 11 through 14 are just some arbitrary transfer functions. Ooh, I have another one. So 11 through 15, I have 5 transfer functions. And the only thing I'm really changing between these is this number sitting right here in the denominator. And you're going to see this is going to have a drastic effect on the damping ratio and alpha. Okay, great. Let's see how this works in terms of poles, etc. So there's 5 functions. I'm going to plot the poles and zeros for all 5 functions on a pole zero map. Pole zero map is really just using the x-axis as the real axis and the y-axis as the imaginary. And then you can plot poles on there very easily. So the first function that I did, and let's look at the numbers here. So equation 11, the first one that I did here is this one. There's 11. All right. Equation 12 is moving in. There's equation 12. There's equation 13 coming in terms of the poles. Here's 14 over here, and here's 15. Okay, you can see what's happening here. I'll put this is 14. This is 15 over here, this green one. And there should be a pole pair for the red one. There's 12, and there's 11 again. So you can see for equation 11, which is the first one, we have 2 real roots. Somewhere minus 2.7 and minus 0.3, let's call it. And then as we move in, the red poles for the transfer function 12, we have 2 and 0.5 exactly. For 13, you actually have 2 roots there at 1, so double root at 1. Now what happens at 14, equation 14 and 15, we no longer have a real root, so we have a complex conjugate pair. So you see the purple there, and then you see the green. Those are complex conjugate pairs. Okay, so that is simply just taking these 5 transfer functions and plotting the poles on the real imaginary axis. Nothing tricky here. But now let's take a look at what this means or how this translates to an actual response of that system. Because all we're doing for now is finding zeros in the denominator and plotting them on a real imaginary. What do these actually translate in terms of the response in the real time? Okay, so let's go to our step response. So in blue, this blue waveform is the step response of our first equation, 11, right? Then we have 12 in red. That's 12. And then yellow. The yellow is a double root at 1. Okay, let's put that in there. And then we have kind of a purple. That's our 14. And lastly, green, we have 15. All right, this is really interesting. Let's take a look at this. So what happens here is essentially the first 3, 11, 12, and 13, those look like nice exponential responses. Well, and indeed they are, and that's because if you look at the roots here, they're all real. So that's e to the minus at when you do the inverse Laplace transform, right? So those are converting right back to natural decays. Awesome. But what happens once you get to, for instance, 14? You see we have a complex conjugate pair. In fact, what are these dotted lines and these radial lines on this plot? Well, this is a very interesting question. Okay, so these radial plots going out like this, these are actually constant lines of damping ratio. Okay, let's translate that back. So all the roots that were on the real axis, that's a damping ratio of 1 exactly. It's perfect damping. Awesome. And you can see all those roots gave us a nice, good response that was clean, a natural decay response. But let's look at equation 14. You see these 2 lines go out here. You're at a damping of, let's say, call it 0.79, something like that. So that's a little bit under damped, which means you're going to get some ringing. That's actually this purple one. So it actually overshoots a little bit and then comes back down and settles. So a damping ratio of 0.7578, it's not that bad. It overshoots a little bit, but it comes down quick. Let's take a look at green, though. This damping ratio is up at like 0.19. See this over here, this constant line? Because it's less than 0.24. That's really underdamped, which means it's going to ring a lot, which is why you can see in our response that green is just ringing a lot. Overshoot, undershoot, overshoot a lot. It takes a long time relative to the other ones to actually settle down over here to 1. So now we kind of have a correlation of what the pole location correlates to what type of response. So the whole motivation for having this discussion is to really show to you that in terms of control, when we eventually get down to it, what we'd like to do is push all of our system poles towards this constant damping ratio of 1. We'd like to move them all here because then we get nice clean responses and that are naturally decaying to what we'd like. And the further we get them out over here in these bad damping ratios, like less than 0.5 or less than 0.6, then we're going to have a really long ringing response. So that's essentially what we want to do, is push the system poles to where we want them. And a lot of it, where we'd like them to be, is close to this constant line of damping ratio of 1. Now these other lines, which I haven't talked about yet here, going this way, this is the natural frequency of the system, these constant lines here. So you can see this is 2.5, 2, 1.5, 1.5, etc. So that gives you the natural frequency response of those poles. Okay? All right. Now, lastly, what we're going to do in terms of these poles and these transfer functions is let's look at their Bode plot. Interesting. If we look at the Bode plot for the first 4, you can see they're pretty smooth in the low frequency. As we get to higher, they roll off at minus 40 dB per decade, which is nice. But look at this. Once we actually get a complex conjugate pole, which is right here, you can see this huge boost in gain. This was for that last system. I believe it was equation 15. And so we have this big kind of resonant response. It's underdamped, so you're going to get some ringing. And you get some ringing at this frequency here, which turns out to be, in this case, the natural frequency, or the resonant frequency. Okay, so just by looking at the Bode plot in terms of gain, we can say, oh, these are nicely damped. These first 4, they're pretty well damped, pretty well behaved. But this last one, we can tell just by looking at the Bode plot, we're going to have some ringing, any type of response. Okay, so you could correlate all these different ways of looking at this to understand what type of response you have and how you can push your system to deliver the type of response that you would like. Okay, so switching gears here. This is a general block diagram for control system. Generally, the plant is a system we're trying to control. In terms of power electronics, that could be a converter topology. It could be a buck, a boost, whatever you want to control. GC, this is what we're trying to design. In general, this is the controller that we want to design to push the system to track a certain objective. For instance, voltage. We want the voltage to be 5. Our controller is trying to drive this plant to be 5 volts. And so a lot of times, for instance, in PWM converters for voltage mode control of a buck converter, U is the control actuation. And in that case, it's just the duty cycle. So the duty cycle goes into the plant, and the plant spits out a voltage. Now, what's H of S? This is just an arbitrary block for your sensor gain. So a lot of times, like if you're sensing out, if you're outputting 100 volts, well, you're not going to feed 100 volts directly back to your controller, right? You're going to knock it down. There's going to be a gain. So you may have like a 1 to 100 gain, 1 by 100. So 100 volts will output 1 volt through the sensor, and that now we can compare 1 volt as the reference to 1 volt as the output of the sensor. Okay, so that will track for the gain of the sensor, but also any type of phase shift or bandwidth limitations you have of your sensor you can incorporate in H of S. Now the reference in general in digital control systems is just going to be a memory location and number. So like if we're trying to track 100 volts, we have a H sensor gain of 1 by 100. The reference somewhere in memory, a digital number, will be just simply 1. Okay. And of course, if you subtract the reference from the output through the sensor, you get your error. That's how much you're off by. So what you're always trying to do in a control system is drive the error to zero. If you're driving the error to zero, that means your output is tracking your reference, which is exactly what you want. So quick overview, GP, it's called the plant. This is always the process you're trying to control. The controller, this is the transfer function you're trying to design to stabilize the system and also to track your objective. Feedback, H of S, in general, this is just sensor gains for whatever you're trying to control. There's going to be some type of gain and phase shift associated with that. Now, when we're trying to actually design GC of S, we have to have some definitions. Now, by the end of this lecture, we won't know how to design a control loop, but just have some general definitions on how to calculate certain quantities that will be useful in finding a controller. So the first thing is we'll define the open loop gain, GOL. GOL is just going to be break the loop right here and multiply your forward gain. So GC of S, GP of S, H of S. That's all it is. The open loop gain. It's if you broke the loop here and you had an open loop, what is the gain of that loop? Now, there's a very good reason we like to find GOL because we can derive a lot of different transfer functions based upon GOL. For instance, the closed loop response. That would be from reference to the output. We can write a transfer function for that, and that's defined here in 17. So that's going to be the forward gain path here, GC GP, divided by 1 plus the open loop gain, which is right here. Now, this is very useful because GCL is, in the previous section, what we're trying to push our system response to. So at the end of the day, you want GCL to have poles that are nice, i.e. damping ratio of 1, and you don't have a lot of ringing, and you can get the type of speed of response that you want. So you're trying to shape, essentially, GC of L, the closed loop response, to push the poles to be where you'd like them as a designer, okay? All right, and there's some other, besides doing that, there are other things you can check, not just the reference to output. You can check the reference to U, the control effort. This is useful if, for instance, it's very expensive to actuate, meaning it's expensive to use U, so you'd like to see how much control effort from a reference input are you using to control your system. Now, in digital control power electronics, if you're adjusting D, in general, 18 wouldn't be used. It's not too useful because it doesn't cost you anything in terms of fuel or anything like that in adjusting the duty cycle. So it just depends on your application, but sometimes 18 can be very useful if it's expensive to actuate. This 19 is very useful, especially for like voltage mode control when you're tracking voltage. You're not really going to have step changes in references because you're just going to fix your reference at an output voltage. But what you will have is a disturbance to the output voltage, so D to Y. And where this comes in is you can put this right here. You can have at the output this disturbance. So equation 19 essentially tracks this disturbance to the output voltage. So if you had a step change in load from 1 amp to 10 amps, this equation 19 would tell you or show you how it would track and where the poles are. Are they well damped? Are they going to ring a lot? So you may want to look at this equation in terms of designing your system poles. It just depends on the objective again. But here's the definition, equation 19, from disturbance to the output. This is generally called the disturbance rejection transfer function. And lastly, a disturbance to control effort transfer function in 20. Again, this is only really used if it costs you fuel or money or it costs you something to actuate, and you really want to control how much you actuate so you're not wasting energy. But what this will give you is your type of response that you will have from a disturbance to the control actuation. Again, may be useful, just depends on your application. Okay, so what makes a stable control loop? Well, if you look at the poles, you want them to be in the left-hand side. That's the first and foremost thing. So if this is the real axis and the imaginary axis, you want everything to be over here, left-hand plane. There's a very good reason for this. The minute you come over to the right-hand plane, you have a pole with a real number. That means when you take the inverse Laplace transform, you have e to, let's say, the 6t. That's your response. Well, if you plot this versus time, guess what? This explodes, goes to infinity. But if you're in the left-hand plane, you always get something e to the minus, say, 6t, which we know will converge to 0 as time goes to infinity. So this is a really simple explanation, but you want everything in the left-hand plane to guarantee stability. Now, stability doesn't mean it's a good control design, but it does mean that your output or whatever, your control effort will not explode on you. All right, so there's different methods to determine stability. You could do a pole zero map, go on the left-hand side. You could do the Nyquist criterion, the Wirth-Hurwitz, or a Bode diagram as well. All these different methods from a control class are valid. A lot of times we'll just check poles or look at the Bode diagram. Closed loop transfer function, again, you want to have them all in the left-hand plane to be stable. In the Bode plot, the way to check stability is when the gain of the open loop transfer function passes through 0 dB, look at your phase. If your phase is more than negative 180 degrees, essentially you have positive feedback and it'll be unstable. But if it's less, then you're stable. So again, it's just another way to check stability, but from the Bode diagram. The phase margin is defined as the amount of degrees that you're away from minus 180 when you cross through minus 0 dB. This has kind of a soft correlation to damping. So if you have a lot of phase margin, you're going to have a pretty well damped system. And again, it's a loose correlation. If you don't have a lot of phase margin, let's say 5 degrees, then essentially you're going to ring a lot. You don't have a lot of damping. So the response of the system is dominated by poles that are closer to the origin in the S-plane. So if you want something that's really fast, you need to push all your poles to the left really far so you can have a really fast response. And the ones that are closest, again, to the origin will dominate the response. Let's see. Yeah, so essentially these sum up everything I talked about in terms of the poles. A lot of times, too, when you push the poles to the left, faster doesn't always mean better. Faster will mean more actuation because you have to push harder on the system to get it to where you want in a smaller amount of time. So just realize that there's always trade-offs there. If you push your poles further to the left, you get a faster response. That's great, but U is going to go way up, your actuation. Okay, this ends the first part of the Intro to Continuous Control in the Digital Power Electronics class. I'm Nathan Weezy. Thank you for your time.